Hey, afternoon, everyone, and thanks for coming to my talk, Getting Rid of the Rest, our migrations to GraphQL. Quickly, I will dive in, covering basically the migrations of how we moved to the Android client on Pinterest for GraphQL. My name is Adam Greenberg. I am a staff engineer at Pinterest. I've been working on mobile for as long as I can remember now. So quick background, just getting familiar with the terminology as before we dive in. GraphQL is a client-driven query language for APIs. When we look at it, assuming most people are familiar with it, but if you allow the comparison, REST is like a restaurant menu. Every feature is a new item on the menu. You can basically choose like a hamburger and fries or salad, but you get basically what is predetermined and pre-delivered for you. They prepare the dish based on a predefined recipe and they deliver it to you. We like to think of GraphQL sort of like a buffet. The server makes all of the data available to the client, and then you basically take what you want. So you can pick a salad, you can have appetizer first, you just want cheese, you can go and grab that. There's only one endpoint and everything's on the menu. So diving a little further, just a little bit more of the terminology, just to familiarize yourself again. The schema is the heart of GraphQL. The shared artifact is among the server and client, so basically it's self-referential and you know exactly how to communicate with the server. It's not executable, but it's more configuration-based. We'll give you all the information you want. Anyone can look at it and learn exactly what's on the schema, what's on the back end, and what sort of pieces can be delivered. So conceptually, the schema is a graph of all entities in the system and how they relate. This is a zoom of our map last year of all our related stuff. It's just kind of a mess. But you were able to see that, with all this, it kind of conceptually can detail how the schema looks. So moving on, types and fields. The schema consists of types and fields. Basically, those are defining the shape of the data so that the GraphQL objects are composed of types, which are composed of fields. Every field has a type of its own, and all data in GraphQL is a scalar or a composite type of the schema. So a quick base overview for kind of how it looks. So if you have like a type user, you can see some basic fields that would relate to that, as well as a sample pin. Generally, these sets are going to be much, much larger in scope, but just a general idea. And we do not have streaming APIs yet, but so the fundamental pieces are the queries and mutations. So basically, this allows you to interact with the schema in the back end in kind of the simple create and update standards, allowing you to return data basically in the same way. And so moving on, just taking a look kind of at our journey at Pinterest. So where we are, we've done the back end migration, we've continued with the API migration, and now we are still slowly moving to the client migration. As you can expect, fundamentally changing the models is basically just a crazy process to do, kind of like while the car is driving, we're basically trying to change the engine. So some updated stats, we've migrated over 7,000 fields, 878 endpoints for our 450 plus million users, and for Android, we had 3 full-time engineers to create kind of the support for this. And so because of this, obviously, we wanted to make sure that we had someone else kind of doing a lot of the heavy lifting for us. And we went with Apollo Kotlin, which maybe if you are here, this is something you're familiar with. So I won't dive in too much of what it is, but basically it's a strongly typed caching client for GraphQL, for Java and Kotlin. It supports Java Legacy, Kotlin first, it's Kotlin multi-platform. And basically what it allows us to do is have all these benefits. It's not only the manager for the API requests, but builds the queries, mutations, subscriptions, gives us normalized caching capabilities, HTTP caching, custom scalar types, auto-persistent queries, and a whole bunch of other goodies, AST parsing, and multiple Gradle plugins to allow us to actually even hook in and do code gen so that we know everything's mapped together. So what this gave us was basically, we wanted this information, and it gives us, like, this is a very high level sample, but just basically gave us these data classes generated based on all of these pieces. So our client migration, from the Android perspective and the iOS perspective, and I guess web to some extent, more mobile web, web has nice resolvers, so they know where the fields map to, and so it's a little easier for the migration. Clients, unfortunately, don't have that. So what we kind of ran into was this big picture problem where things are pretty straightforward in REST. You know, you have a user model, you have it for your first screen, you pass it to your second screen, and that screen, that works together. It's gonna handshake well, you know that the fields are there. There's sort of nuances about some things, but it works. Where with GraphQL, now we have the data that we request and only the data that requests, and so that gets mapped to a model. And so when we get a user screen with the user screen data for A, and we try to pass it to the second screen, because the shape of the data is different, that no longer works to basically allow us to have kind of that standard communication. And so the big picture problem for us kind of became, how do we create reusable components? How do we handle these interactions? How do we handle subscriptions? How do we handle observability and statefulness? And how do we perform all this fast and efficient in a constant pattern just to make sure that it is effective and interops with REST? What we found out was the general approach and our first approach kind of looked like define your domain models, expose a store API in a shared way, allow that to communicate between each other, and then abstract the data, lift up everything, and make sure that there's kind of this abstraction layer. And then basically you can have some sort of gate that's going to switch between the REST and GraphQL layers in that final layer. And so what we tried to do this was getting kind of clever. We took a look at our REST model, and we did some annotation processing. And so we basically built these kind of converter models with this abstraction layer, and it abstracted everything into an interface. And then we had this piece sitting on top of each other so that it kind of would generate something that would map between the Apollo model we have here and the REST model. And then this would kind of sit between everything else. And this didn't work for us. It may work for you. It's worked for a number of companies. We talked with a bunch of people while doing this. It went very well for them, but what it basically did was we really saw it adding this massive additional layer. Our goal is to move off of REST. We want to move to GraphQL for almost every endpoint that it makes sense. So we were ingraining support for that in the model. The number of sheer classes was just tremendous because with every GraphQL request, you're getting a separate model except for shared interfaces and pieces like that. So we would have something like there's 100 surfaces which use some sort of variant of the user model, and we'd have like a 1 to 100 mapping, and that just became unmanageable. And again, there's no way to handle this conversion cleanly because you need 100 converters for each of them, and then an end-to-end for every single piece with GraphQL, and then it's introduced multiple points of failure, right? So people are iterating on surfaces, you have to maintain 2 pieces now, and now it just is not basically functional. So our current architecture became this piece where we just decided against this abstraction and basically thought that, what can we do to make this so it communicates well? So basically what we did was we wanted to de-scope our problem and isolate as much as we could, recreating screens as we migrated, but sooner or later you're still going to run into that big picture problem. I mean, immediately pretty much, but where you just need to basically communicate with surfaces, components, data stores, and anything else that integrates with it. So sometimes we just want to let it be someone else's problem. Again, we wanted to move quickly, and we found a way with the Apollo Kotlin client. Basically, the principles still apply everywhere else, but I thought it was really clever. So we're basically using what we've already got. So again, this is kind of the shape of the object that we're querying, and then we get the results back in that same manner. So if we take a look at that, that was the query. We get back the data in this JSON shape, and then basically that interprets it to this data class. Now, what happens now is that GraphQL uses, Kotlin, Apollo Kotlin uses this normalized cache, where it's going to normalize all this data and store it into a cache, either in memory and then or on device. But all the data is normalized so that it can be related somehow. Each of these pieces have a type name and an ID. So we have these unique identifiers on every single type, and therefore we can basically make sure that when we get it normalized, it looks something similar to this, where we have kind of a favorite book author, query root. where it has these kind of cache references. And through the normalization process, we saw that this basically was allowing us to basically take these kind of data classes and go back to that user object. We could see that it was normalized to something like this. And so we had these normalized pieces in the cache. Once it was all normalized, we could see very clearly that this concept could then apply to our user model from REST. And so with this, we were basically able to kind of start to put together the pieces of how we could go back and forth. And so then basically looking at that normalization in non-GraphQL, you could see that there's some sort of mapping together. And so very technical heavy from the docs. With the normalized cache and properly configured cache IDs, the updated type is automatically merged with the existing cached item and was returned from a query of that type. So therefore, we discovered that if we basically took a all-knowing or kind of God query object that has all the fields for that type, we can map between the two pieces of information. So if we have two separate queries on that same type, like that book object where you see the authors and the different fields, but some overlapping. If we combine them together into this kind of all-encompassing God query object, now we have all the fields that are being requested for the whole app. And so you can see all the fields shared in both queries, all the fields used in all queries. And we could basically then take this and map it to our REST object. And you see that there's a set of it. So there's some overlapping fields, some junk, some jank. We may not want anymore, but if we're making queries on this object, we don't want to overfetch, so we only want to request the minimal amount of data. So that allowed us to basically solve this one-to-n REST problem. So basically what we're going to do now is register a single converter that knows how to go from REST to Apollo. Convert to Apollo, convert to REST, and then we can create that for that God object. And then basically take a REST converter that allows us to take our repository, take the type name, the converter, and the query for each of these and map these into some sort of dictionary lookup. And then we register these at build time and then basically have an information of all these mappings. So at a very high level, what this looked like was us hooking into the write operation for the normalized class, making a callback, looking up from our dictionary to convert the two of them based on the type name. Again, the type name's unique for each of these types. And then basically looking at that connection object, reading from the cache, and then converting it to REST. And so basically any single book object now could be converted to that God object. That God object can then take a single converter and map it to the REST object and then shove it out to the rest of the app. So we have a way to communicate between that edge on that surface. And so now we have that down. I know I only have 20 minutes. I'm kind of flying through everything, so apologies for that. But we can do it in reverse. And so we're doing the same thing, basically. We are observing for updates for Apollo on a flow, which allows us to basically subscribe and listen to all the events being emitted. We flip the process, basically, so that we can now update Apollo systems from the REST update. Again, we're looking at that connection object. And this basically knows, again, how to take that model, the query data, and then the query itself. And so a little more technical here, but we're taking that query object. We're making a node query on that node ID. We start by getting that node identifier. And then we're going to use that to look up the specific node's query object. It generates this node, which contains all the fields of the type given an ID. The yields query lookup. And we can take that query lookup basically to use that connection, again, to convert now from REST to GraphQL. When mapping those two things together, we get a ability to now take that query and then normalize it with the query data, which gives us that normalized record set. And now that we have all of that, basically, we can merge that into the data process, which kind of then will give us that query God object. And then taking that giant all-encompassing piece of data, we can now basically, we have that query, the data class is mapped from this, and then we can map it back to the REST model, communicate it to the app, and then we have that. So we have a way of kind of communicating those fields back and forth. We basically note everything. If it's null, we don't set it, and we have like it is set. So you know that there's like a non-null specific piece. And then we're able to handle that. And so what this still left us with was kind of this end-to-end GraphQL to GraphQL problem. And we haven't fully solved that or built anything 100%, but we kind of left this up to the developer because we really felt it was up to them to use kind of the GraphQL way of doing things, creating separate fragments that basically will share that data internally and talk to each other the right way so they're more conscious and understanding of the data, which will allow them to basically move between sharing different models of the same type between different surfaces. I know that was pretty rapid fire. I think I have a couple minutes left. So please, any questions, anything I can go over again, I'll be happy to dive into more deeply. But thank you.